Okay, thanks, Sylvia. So I guess I'll start by stating the conjecture. And this was a conjecture by De-Giorgi in 1978. All right, and it concerns these bounded solutions. So if we let U in C2 of Rn be a solution of what is known as the Kahn equation. So Laplacian U equals U cubed minus U. And it also satisfies, so it's bounded. So U is less than or equal to 1. And then it's monotone in one direction. So all this in Rn. Then he conjectured that all the level sets of U are hyperplanes if n is less than or equal to 8. Okay, now there's our goal, because it seems kind of random right now. So our goal today would be to arrive at this conjecture ourselves, and this will take us down a road where we'll see many different parts of mathematics. So the first part we'll see is gamma convergence. Very briefly touch on it and give you the idea behind what gamma convergence is. And then, as the title of the talk says, we'll then have to look at some minimal surface theory to see, well, where does this n less than or equal to 8 piece of information come from? And then, well, we'll also need to see a bit about the Kahn energy functional, right? Which is the energy functional corresponding to this equation. So this here is the Euler-Lagrange equation of this energy functional. And then we'll finally see how these three different areas meet in this De-Giorgi conjecture. And then hopefully in the end, we'll give some results on the conjecture. So the first section is called gamma convergence. So suppose you have some minimization problem. We'll call it M naught. Okay, and it's to find the infimum of some function f naught of x. This is a functional defined on some metric space x. So we're minimizing it over values in this metric space. So, and then suppose also you have a sequence of minimization problems. Let's call them M epsilon, where you're looking to minimize these different functionals, f epsilon of x, over the same space, x equal x in x. Okay, and suppose that f epsilon converges pointwise to f naught as epsilon tends to 0. Okay, can we then expect, the question is, can we then expect that the minimizers also converge, so that M epsilon converges to M naught? And in general, no. The answer is no. So let's look at a really simple example together. So let's say let's define f of u to be the integral from 0 to 1 of 1 minus u prime squared dt. Okay, and then we'll define the constant sequence f epsilon of u to be f of u, and we're going to minimize over all possible functions u on 0, 1. So if really we're looking at for functions of class h1, this isn't so important. So if you don't know what h1 is, don't worry too much. All right, so let's look at this. So clearly, minimizers of this guy, it has a minimum value of 0. If we choose u prime, okay, to be plus or minus 1. So minimizers could look like this. This is 1/2, this here 0, this is 1, right? And well, over here, the gradient is 1, and over here the gradient is -1. Okay, and this clearly minimizes this guy, because if you sub this into f, you'll get 0. Okay, but any function that has gradient only plus or minus 1 will minimize this. So also, this guy here, let me draw. This guy here, let's call this M2, okay, minimizes this functional as well. So if I call this one M1, I can then also create a third minimizer. Trying to, that zigzags like this. All right, and it still has gradient +1, -1 everywhere. This will also minimize the functional. So we can call this M3. Then clearly, M1 is a sequence of minimizers, right? Okay, so M1, 2, 3, 4, and I can keep creating this sequence like this, just taking more zigzags, right? So we can call this sequence M epsilon, and this M epsilon converges to 0, and 0 does not minimize this functional. So this is a really simple example to show that pointwise convergence is not enough to say that, well, minimizers converge to a minimizer of your limit functional. So we need a different notion of convergence if we hope to have that minimizers converge to a minimizer, right? And clearly, this notion of convergence isn't going to satisfy a constant sequence converges to itself, right? So with this we define, it's called gamma convergence. And with the notation above, we say that f epsilon gamma converges to f naught. I called it m naught, f naught, right? So we say that f epsilon gamma converges to f naught, which I write like this, if the following two conditions hold. So we have, for every x in x and any sequence, say x epsilon, epsilon greater than 0, in x with x epsilon converging to x, okay, we have the lim-inf inequality. So f naught of x is less than or equal to the lim-inf. So epsilon converges to 0 of f epsilon of x epsilon. And then we also need to have the existence of a recovery sequence. So for any x in x, there must exist one sequence right? So there exists only one sequence in X with, well, such that X epsilon converges to X and F naught of X is greater than or equal to the lim sup as epsilon converges to 0 of F epsilon X epsilon. And so if you pair this and this together, you actually see that, well, the second condition is that there is at least one sequence along which we get convergence, right? We get convergence pointwise, okay? And so this definition of gamma convergence, okay, along with some equicoercivity assumption on F epsilon, that's not too important for us, but this is enough to guarantee that minimizers of this sequence converge to a minimizer of your limit. Okay, so that's the first aspect that I wanted to talk to you about. Just very briefly touch on what gamma convergence is. Then the second aspect that we need to talk about today is a little bit of minimal surface theory. And there are many different frameworks to approach the theory of minimal surfaces in. So for today, we're going to fix one framework, and that is the setting of sets of finite perimeter. Okay, the idea of this framework is that we consider n-1 dimensional surfaces as the boundaries of sets in Rn. Okay, so as an example, we can consider the sphere embedded in R3 as the boundary of the unit ball in R3. So this is just a really simple example. So consider the sphere as BB1, where B1 is the unit ball in R3. So where okay, now given any F, okay, so given any F in C1 compact support R3 into R3, okay, we can write via the divergence theorem. So we can write by the divergence theorem or the Gauss-Green theorem. So that the integral over B1 of the divergence of F dx is equal to the integral over the boundary of B1 of F dot n d sigma, where sigma is the surface area element on the ball and n is the outward unit normal. Okay, and note that this really relied heavily on the fact that the boundary of B1 is a smooth surface, right? Because if it wasn't C1, at least we wouldn't be able to define this guy, right? Because recall that this guy, this outward unit normal, is defined as the derivative over, well, the norm of the derivative, or the gradient of the norm of the gradient of the function defining your surface. So we really, this step here really needs some sort of regularity. All right. But let's just move on. This will come back later. Let me now say that if I take the supremum of both sides over all, say, f, all such f that satisfy, well, with L infinity norm. So let me just write it like this. So the L infinity norm of any f that I consider should be less than or equal to 1. What do I get? Well, I get on the left side, this guy just becomes this, nothing changes. But then on the right, this supremum is something that we know, right? This supremum is the area of the ball. I can cook up a function such that this guy is 1 all over the ball. Okay, and so if this guy is 1 all over the ball, I just get the surface area of the ball. Okay, and so I'm going to represent the surface area of the ball like this. But this, like I said up here, this really needed some regularity to see this. Okay, but this over here doesn't need any regularity at all to compute. Okay, and so in order to generalize this idea, or in order to generalize this this computation, we make the following definition. Okay, so we define the perimeter of a set E in Rn, okay, or perimeter, because geometrically this is what it looks like, but really this is just the area of the boundary of E. This is actually what it is intuitively. We define it to be the function P of E to be the supremum of the divergence of f x, where we take the supremum over all f with L infinity norm less than 1 and f in C1 compact support of Rn into Rn. Okay, and so whenever E is of class C1, or the boundary, well, has C1 boundary, we recover the usual notion of area, just like we did in this specific example, right? And so we say that if E satisfies, write it like this, so satisfies P of E is less than infinity, okay, we call E a set of finite perimeter. Okay, and then we say that E is a minimizer for the perimeter if we have the following two conditions. So given a family of deformations, this is just some functions that deform your intuitively. The idea is that these functions will just deform your set and change the way it looks in some compact set. And then we say that E is a minimizer for the perimeter if the following two conditions hold. So this is called stationarity, or any E that satisfies this is stationary. And then we also need stability. So the second derivative V is greater than or equal to 0. And this is actually just from one-dimensional calculus. If you wanted to look for minimizers, these are the two conditions you check, right? You check that at this point, the derivative of the function is 0, and then that the second derivative is positive. Okay, so it's concave up. Okay, so this is all this is saying. Okay, and then we can ask ourselves, well, can we classify all global minimizers for the perimeter function? So what do global minimizers look like? And well, they are hyperplanes if n is less than or equal to 7. But if you add some extra structure to the surfaces that you're considering, and you say, okay, I only want to consider graphs. So if the surfaces are graphs, then minimal graphs are hyperplanes if n is less than or equal to 8. Okay, and this we can start to kind of see maybe where De-Giorgi got this idea that n has to be less than or equal to 8. But we'll get to that in a second. I just want to give you a reference for where these results came from. This is from a paper of Bombiri, De-Giorgi, and Gusti in 1969. Okay, so good. This is all the background we need about the perimeter functional and minimal surfaces. And now that we have this, we can talk about the Kahn energy functional, for which the Kahn equation that appears in the De-Giorgi conjecture is the Euler-Lagrange equation. So we say that the Kahn energy functional is the Dirichlet energy plus this potential. This is just one specific type of potential. There's other, you can replace this with the more general type, but this is the specific one we'll consider today. Okay, and we can say that U minimizers, so U minimizes 1, well, if and only if Laplacian U equals U cubed minus U. Now, the conjecture is concerned with entire solutions. So we'd really like to study solutions that are defined on all of Rn. And there's a neat trick, there's a really neat trick to study this. Okay, and this is called, to study this in a ball, right, on a small domain. So we don't have to look at all of Rn. So say this is a ball of radius 1. Okay, and then your entire solution kind of looks like this. This is say, I'll say this is a level set. Say this is like u equals 0 some or so. Okay, and then what we can do is a blowdown, okay, which shrinks more and more and more of your solution into your ball of radius 1. So we consider u epsilon of x is equal to u of x on epsilon. And so in your ball of radius 1, you now have, say, more of your solution, but they're still entire, so they still exist outside this ball, but you've kind of pushed it all into, where you pushed more and more and more of your solution into this ball. Okay, and so going with this trick to study entire solutions, we can see that the blowdowns u epsilon then minimize what's known as the penalized energy in the ball. So relation v squared on 2 plus 1 on epsilon 1 minus v squared on 4. Okay, and so now we can see that, all right, we have a sequence of functionals that we'd like to minimize. So referring back to section 1, where we discussed about gamma convergence, maybe there exists some sort of gamma convergence result telling us what these functionals gamma converge to, and this is true. So this is a theorem of Modica Mortola from 1977, so 1 year before De-Giorgi stated his conjecture. They say that suppose above E epsilon of U epsilon is less than or equal to C, where U epsilon is a sequence of minimized these blowdowns that we've defined up here. And then up to subsequences, U epsilon converge to U with respect to, well, the L1 loc convergence, and the functionals E epsilon gamma converge to some multiple of the perimeter functional of the level set U equals 1. Okay, and they also tell you that whatever you converge to, so this U here, with U is equal to the difference between two characteristic functions, Rn, so chi e minus the complement of E, where E is a set of finite perimeter. Now, once we have this, well, we can paste all these bits of information together in the De-Giorgi conjecture. So this is our final section. So the De-Giorgi conjecture. So we know that so far, the story so far, is that we do this blowdown procedure with these level sets, okay? And then we see that the minimizers, well, the blowdowns, okay, are minimizers of this functional for each epsilon. This forms a sequence, and this sequence gamma converges to the perimeter function. So, and if this U is a minimizer of the perimeter functional, then we know from this section up here that if n is less than or equal to 7, it's definitely going to be a hyperplane. Okay, but we want to get into the n is less than or equal to 8 setting, right? And this is where this monotonicity in one direction criteria comes into play. Okay, so you can think of, say, this is x prime in Rn minus 1, and this here is xn. Then if this is the level set of, say, u is equal to 1, then with respect to Rn minus 1 variables, this level set is a graph, okay? Because dn u is strictly positive, right? There's no way to intersect, like, there's no way to intersect, like a vertical line will intersect this level set twice, just because of this condition here. And so, since we are in the minimal graph setting, okay, we can conjecture, as did De-Giorgi, okay, that the level sets of these blowdowns converge to a hyperplane. Okay, and well, we know the level sets of these blowdowns must converge to a hyperplane, and then, well, what do the level sets of these blowdowns look like? So, since u epsilon is equal to 1 is the level set of the blowdown u epsilon, this guy is actually equal to epsilon times the level set of u equals 1. And so if these level sets must converge to a hyperplane, right? These guys converge to a hyperplane, but this is just this, right? Then it's pretty safe to conjecture that this level set here must be itself a hyperplane. Okay, and so now that we've arrived at the De-Giorgi conjecture, and we've seen some nice areas of mathematics, I'll just state its resolution. So in low dimensions, so resolution in n equals 2 and n equals 3. Okay, and this, well, it was first done by Gusup and Goy. By studying Schrodinger operators in 98, so 1998. But then, well, and this was only in n equals 2. But then Ambrosio and Cabret proved it in n equals 3, and the same method also works in n equals 2 in 2002. Okay, and so I'll briefly tell you about how they did it in this paper. they relied on the following Liouville type result from a paper released in 1997 by Sticky, Caffarelli, and Nierenberg in 1997. Okay. And they had the following result. They said let phi be in L infinity log of Rn be positive, and suppose that sigma in H1 log of Rn satisfies sigma greater than 0 in Rn in the distributional sense. Okay, and we have this following condition that phi sigma squared less than equal to C R squared for any R greater than 1. And then if this is true, then sigma is constant. And really in the paper, the key step in both, well, the key step is showing this. It's showing that this guy holds true for suitable phi and sigma. So the idea is, and you can try this, it's not too hard, is that if I define, say in dimension 2, if I define sigma to be the first derivative in of u divided by the second derivative of u, and this is well defined because in 2 dimensions, so in 2 dimensions, we are assuming that the second derivative of u is not is strictly positive, okay? And then if you define phi is equal to d2u, okay, then the proposition, just apply it to this, will be will give that sigma is a constant, okay? And if sigma is a constant, some constant, then it follows that, well, d1u is equal to some constant, let's call it c, d2u. And so u is constant in the direction one minus c, and hence u of x is just a function of one variable. So g of a dot x for some function g, where a is the vector c1. And since u is a function of this one variable, then this, you can conclude from here that the level sets are indeed hyperplanes. And the idea is also the same in dimension 3. So instead of considering just sigma, this sigma, where d1 over d3, you also consider d2 over d3, and then you hope to apply this result. And yes, that is the end of all I wanted to tell you. And if there are any questions, I'd be happy to try and answer them.
Art really looks like kinetic energy or something like that, like the, yeah, like the 1/2 of value of v squared.
Yeah.
Looks like kinetic energy. And do you have like an interpretation for the second term?
Yeah, so this is a double well potential energy, right? So this is really this is like an application in physics. So you're right. This would be a kinetic energy, and this here is a potential energy that looks something like, I guess, -1 one that looks something like this. And this is the, well, it has a name, and I can't really remember what the name is at this moment.
But it's some sort of potential energy.
Yeah, exactly.
Okay,
it's some sort of potential energy.
Okay.
Yeah.
Makes sense, yeah.
Yeah, and in fact, this is like this is the basic kind of structure of a Schrodinger operator, right? Like if you compute the where is it? The Euler-Lagrange, yeah, here, right? So in the first paper of Gusup and Goy, the way they attack this problem is to consider this as an Schrodinger operator, where this was the potential function. Yeah. Oh well, this was the potential function, and then this is its derivative. So yeah. Oh, Dana is asking who was the supervisor and which lecture was your thesis based on? So this was a semester paper. I did it under Professor Carlotto. And it wasn't really based on a lecture. I think I was just interested in a few different things, and I asked him if he knew anything I could read about, and he suggested this. I hope that helps. All right, sweet. Okay, yeah, great question. So the problem is that this condition, where is it? Okay, I lost the proposition. Okay, the proposition is here. So this condition can only be verified when n is less than or equal to 3, right? There is, well, yeah, like they wrote in their paper that there is no way that they said they realized that there was no way to verify this in higher dimensions. Then in the paper that they referenced it from, so Beres-Sticky, Carafarelli, and Nirenberg, right? They asked whether you could relax it, and instead of having this, right, could we just assume that phi sigma was only in L infinity? So phi times sigma is just in is just bounded, right? And if the answer was yes, okay, then because U is in C2, and then on, well, L infinity lock, right? That's important. So if the answer was yes, okay, that all you needed was phi times sigma to be in L infinity lock, then because the derivatives are bounded on compact sets, this would confirm the conjecture in all dimensions, right? But clearly it's hard for that to be true. However, in the paper of Gusup and Goy, they showed that for n greater than or equal to 7, that you cannot relax this. And then later on, someone else also said for you can't relax this condition for n greater than or equal to 3. So it's really this step here. And in dimension n equals 3, showing that this step holds was also really hard. So, and there is no hope to use this method for higher dimensions.